Have you ever wondered what really happens when you flip a light switch and the bulb glows instantly? It feels like magic, but behind that simple action is a vast, complex system working tirelessly to deliver electricity to your home. Today, we're going to unravel this mystery and explore the backbone of modern life, the power system. Whether you're just starting out in electrical engineering or prepping for exams, this video will give you a clear, practical understanding of how electricity travels from its source all the way to your wall socket. Let's get started. Power system is the complete network that generates, transmits, and delivers electrical energy. It's the foundation of everything in electrical energy engineering. This system connects the place where electricity is produced, like a power plant, to homes, universities, and factories. It's a vast, interconnected network that ensures you have power whenever you need it. Understanding this system is crucial for anyone interested in how our modern world functions, and it's the first step in mastering electrical engineering concepts. Make the power system easier to understand, let's compare it to city's water supply. Imagine a reservoir storing water, large pipes carrying it across the city and smaller pipes bringing it into your neighborhood. The tap in your home is where you finally use it. The electrical system works in a similar way. The power plant is like the reservoir, transmission lines are the large pipes, distribution lines are the smaller pipes, and your wall socket is the tap. This analogy makes it much easier to visualize how electricity flows from generation to your home. Remember this phrase: generate, transmit, distribute. These are the three key stages of any power system. Generation is where electrical energy is created. Transmission is the process of moving electricity over long distances. Distribution is the final step, delivering electricity to homes, businesses, and factories. Every part of the power system fits into one of these three stages, and understanding them is the foundation for everything else you'll learn in electrical engineering. Let's start with generation, the first stage of the power system. This is where electrical energy is created. There are three main ways to generate electricity: hydropower, solar power, and thermal power. Hydropower uses water flowing through turbines, solar power uses photovoltaic panels to convert sunlight, and thermal power burns fuel like gas or coal to spin turbines. Each method has its own advantages and challenges, but all produce alternating current AC at a specific voltage, ready for the next stage. Hydropower is one of the oldest and most reliable ways to generate electricity. It works by channeling water through turbines, which spin and generate electrical energy. Many countries rely on hydropower as a major renewable energy source. It's clean, efficient, and can produce large amounts of electricity, especially in regions with abundant water resources. Hydropower plants are often located near rivers or large dams, making use of natural water flow to keep the turbines turning. Solar power is the fastest growing energy source in the world. Photovoltaic panels convert sunlight directly into electricity, making it a clean and renewable option. As technology improves and costs decrease, more homes and businesses are installing solar panels every year. Solar power is especially valuable in sunny regions, and it's helping to reduce our reliance on fossil fuels. The future of energy is looking brighter thanks to solar innovation. Thermal power plants generate electricity by burning fuels like gas or coal. The heat produced spins turbines, which then generate electricity. While thermal power is reliable and can produce large amounts of energy, it also has environmental drawbacks such as emissions and fuel consumption. Despite these challenges, thermal power remains a major part of the world's energy mix, especially in regions where other resources are limited. No matter how electricity is generated, whether by water, sunlight, or fuel, the output is always the same: alternating current or AC electricity at a specific voltage level. This standardization makes it possible to connect different sources to the same grid and ensures that electricity can be efficiently transmitted and distributed. AC electricity is the backbone of modern power systems, making it possible to power everything from homes to factories. Once electricity is generated, it needs to travel long distances to reach cities and towns. This is the transmission stage. Transmission lines are like the highways of the power system, carrying electricity from remote power plants to urban centers. These lines are supported by giant towers and are designed to handle very high voltages, making long-distance energy transfer efficient and reliable. Key question in power engineering is: why do we transmit electricity at such high voltages like 115, 230, or even 500 kilovolts? The answer lies in efficiency. According to the formula P equals I squared R, power lost as heat increases with the square of the current. By transmitting at high voltage, the current is much lower, which means energy losses are dramatically reduced. This is why those massive towers carry electricity at hundreds of thousands of volts. Transmission lines are the backbone of the power system's long-distance network. They stretch across countries, connecting power plants to cities and industrial centers. These lines are built to withstand harsh weather and carry electricity safely and efficiently. Substations along the way help manage and regulate the flow of electricity, adjusting voltage levels and ensuring stability and reliability across the entire network. Substations play a critical role in the transmission stage. They act as control centers, managing the flow of electricity and adjusting voltage levels as needed. Substations ensure that electricity remains stable and reliable as it travels across vast distances. Without these key nodes, the power system would be much less efficient and far more prone to outages and instability. By the time electricity reaches your neighborhood, it needs to be stepped down to a safe, usable voltage. This is the distribution stage. Transformers are used to decrease voltage levels, making electricity safe for homes and businesses. The journey typically involves several steps, from the power plant to high-voltage transmission, then to local distribution, and finally to your wall socket. Each step is carefully managed to ensure safety and reliability. Transformers are one of the most important devices in electrical engineering. They can increase or decrease voltage levels as needed. At the power plant, a step-up transformer raises the voltage for efficient long-distance transmission. Near your home, a step-down transformer reduces the voltage to a safe level. This process ensures that electricity can travel efficiently and arrive safely at its final destination. Typical voltage journey looks like this. The power plant outputs between 11 and 25 kilovolts. A step-up transformer increases this to between 115 and 500 kilovolts for long-distance transmission. A step-down transformer then reduces it to 11 kilovolts for local distribution. Finally, another transformer brings it down to 230 or 400 volts for use in your home or building. Each stage is essential for efficient and safe electricity delivery. Wall socket in your home is the final endpoint of the entire power system journey. After traveling through power plants, transmission lines, substations, and transformers, electricity arrives at a safe, usable voltage. This is where you plug in your devices and appliances, relying on the power system to deliver energy whenever you need it. It's a seamless process that most people take for granted, but it's built on decades of engineering innovation. Every single thing that runs on electricity, your phone, your laptop, the lights in your classroom, the machines in a hospital, depends on the power system working perfectly every second of every day. That's why electrical engineers are some of the most important people in the world. They design, maintain, and improve these systems to keep our modern world running smoothly. If you're studying electrical engineering, you're training to become one of the people who keep the lights on, literally. Understanding the power system is the foundation of your education. Every concept you learn builds on this knowledge, from basic circuit analysis to advanced topics like smart grids and renewable energy integration. Mastering the power system will make every other topic easier to understand. Let's lock in the 3 key takeaways from today's lesson. First, a power system has 3 main stages: generation, transmission, and distribution. Every component you'll ever study fits into one of these 3 stages. This simple framework will help you organize your knowledge and understand how everything fits together. Second, high voltage transmission reduces energy loss. Thanks to the formula P equals I squared R, we know that lower current means lower losses over long distances. This is why power systems use high voltages for transmission. It's all about efficiency and minimizing wasted energy. Third, understanding the power system is the foundation of everything in electrical energy engineering. Mastering this topic will make every other subject easier, from basic circuits to advanced smart grid technology. It's the starting point for your journey as an electrical engineer.